Good morning, everyone. I'm Kanaklakshmi RH, and today I'll be presenting on the topic electronic transitions in organic compounds. This is the important concept in analytical chemistry because it explains how organic molecules interact with UV and visible radiation. We know that whenever an organic compound absorbs energy, their electrons move from lower energy levels to higher energy levels. These movements are called as electronic transitions. Understanding this concept is essential because it forms the basis of UV visible spectroscopy, which is widely used for chemical analysis. In this presentation, I will explain the different types of electronic transitions, their significance, and their analytical application. This slide here shows the table of contents. Now let us begin with the basic concept of electronic transition. As shown in the image, electrons in organic molecules normally remain in their stable lower energy levels, which are called the ground state. When UV or a visible radiation falls on the molecule, the electron absorbs that energy. Because of this absorbed energy, it jumps to a higher energy level, which is called the excited state. This upward movement shown in the image is known as electronic excitation. However, the excited state is unstable. So, after a very short time, the electron returns back to its original lower energy level. This process is known as relaxation. So, electronic transition are important because they explain how organic compounds absorb light. This forms the basic principle of UV visible spectroscopy, which is widely used for molecular analysis. Now, let us understand why organic compounds undergo electronic transitions. As shown in the image, organic molecules contain different types of electrons, such as sigma electrons, pi electrons, and non-bonding electrons. These electrons can absorb energy when UV or a visible radiation falls on the molecule. Once sufficient energy is absorbed, the electrons move from lower energy orbitals to higher energy orbitals. The image also shows electron movement within the molecule, which represents excitation. Whether a compound undergoes electronic transition depends mainly on its molecular structure. Compounds with double bond, lone pair electrons, or conjugated systems absorb radiation more easily. Another important factor is conjugation. When electrons are delocalized over multiple atoms, the energy required for excitation becomes lower. This is why highly conjugated organic compounds show stronger absorption. This explains why different organic molecules absorb radiation differently. To understand electronic transitions more clearly, we need to understand molecular orbitals. The image on this slide shows the different energy levels of molecular orbitals. At the lowest level, we have sigma bonding orbital, which is highly stable. Above that is the pi bonding orbital, that we have the non-bonding orbital, which contains lower pair electrons. At high energy levels, we see that pi antibonding orbitals are also called as pi star and the sigma bonding anti-orbital called as sigma star. And electronic transitions occurs when electrons absorb energy and move from this lower energy orbitals to higher antibonding orbitals. This image helps us to visualize this upward movement. The energy difference between these orbitals determine how much radiation is needed for excitation. A larger energy gap requires more energy while the smaller energy gap requires lesser energy. This orbital arrangement forms the foundation of understanding all electronic transitions. Now that we understand molecular orbitals, let us look at the major types of electronic transition. The image on this slide gives a comparative overall of all the four transitions. The first is sigma to sigma star transition, where an electron moves from a sigma bonding orbital to sigma antibonding orbital. The second is N to sigma star transition, where a non-bonding electron moves to a sigma antibonding orbital. The third is pi to pi star transition, where a pi electron is excited to a pi antibonding orbital. And finally, we have N to pi star transition, where a non-bonding electron moves into a pi antibonding orbital. As shown in the image, each transition requires different amount of energy depending on the energy gap between the orbitals. This difference in energy determines the wavelength region where the absorption occurs. Understanding these transitions are very important because they helps us to interpret UV visible absorption spectra and analyze the molecular structure. Let us first look at the sigma to sigma star transition. As shown in this image, the electron initially exits in the sigma bonding orbital, which is a very stable low energy orbital. When the molecule observes high energy UV radiation, the electron gets excited and moves to sigma antibonding orbital, shown at the higher energy level. This upward movement represents sigma to sigma star transition. The image also shows saturated organic compounds such as methane and ethane, where this transition commonly occurs. These compounds contain only stigma covalent bonds, which are stigma bonds. Since stigma bonds are very strong and stable, a large amount of energy is needed to excite these electrons. That is why this transition occurs only in the far UV region, generally below 200 nanometers. Because of this very high energy requirement, it is not commonly observed using regular UV spectroscopy. However, it is important because it represents the highest energy electronic transition. Next, let us look at the N to sigma star transition. As shown in this image, this transition occurs in molecules containing lone pair electrons such as alcohols, amines, and ethers. The example shown here is ethanol. The oxygen atom contains lone pair electrons which occupy non-bonding orbitals. When an UV radiation falls on the molecule, one of these electrons absorbs energy and gets excited to the sigma antibonding orbital. The image clearly shows this upward electron movement. Compared to stigma star transition, this requires lesser energy because of non-bonding electrons are already to a relatively higher energy level. That means the energy gap is smaller. This transition generally occurs in 170 to 260 nanometer region. Since it occurs in a measurable UV region, it is more useful in analytical chemistry. This transition is commonly observed in compounds containing heteroatoms like oxygen and nitrogen. Now, let us look at the pi to pi star transition, which is one of the most important electronic transitions in organic chemistry. As shown in this image, this transition occurs mainly in unsaturated and aromatic compounds such as ethene, butadiene, and benzene. These compounds contain double bonds, which means they have pi electrons. The electrons initially occupies the pi bonding orbital shown at the lower energy level, and when a UV radiation is observed, the electron gains energy and moves to pi antibonding orbital or pi star orbital. The image clearly shows this upward excitation. This transition requires moderate energy because the energy gap between pi to pi star orbitals is smaller than stigma orbitals. It generally occurs in 200 to 400 nanometer region. The image also shows the effect of conjugation. As conjugation increases, the energy gap decreases, making excitation easier. This is why highly conjugated compounds observe at longer wavelengths. This transition is very important because it produces stronger absorption peaks and it is widely used in UV visible spectroscopy. Now, let us move to the final type of electronic transition, which is N to pi star transition. As shown in this image, this transition commonly occurs in carbonyl containing compounds such as aldehydes and ketones. The oxygen atom contains lone pair electrons, which occupy non-bonding orbitals. And when the molecule observes radiation, one of these electrons gains energy and moves to the pi antibonding orbitals or pi star orbitals. The image clearly shows this upward excitation of the orbital, and this transition requires the least amount of energy among all four electronic transitions. This is because the energy gap between the non-bonding orbital and the pi antibonding orbital is very small. That is why this transition occurs at longer wavelengths, usually between 250 and 600 nanometers. The image also highlights that a transition provides weaker absorption compared to pi star transition. This is because it is partially forbidden according to spectroscopy selection rules. Even though it is weaker, it is very important for identifying carbonyl compounds and studying molecular structure. After studying all four transitions individually, this slide compares their relative energy requirements. The graph shown here makes this comparison very easier. The tallest bar represents stigma to stigma star transition, which requires the highest amount of energy. This is because the energy gap between them is very large. The next bar represents N to stigma star transition, which requires slightly lesser energy. Then comes pi to pi star transition, which requires moderate energy. Finally, the shortest bar represents N to pi star transition, which requires the least energy because it has the smallest orbital energy gap. The image also shows the wavelength trend. As the energy requirement decreases, absorption wavelength increases. This is because energy and wavelength are inversely related. So this comparison helps us to understand why different transitions appear in different regions of the UV spectrum. It also helps us to predict the molecular absorption behavior during analysis. This slide explains the effect of conjugation on electronic transition. The image compares three molecules, ethene, butadiene, and hexatriene. As we move from ethene to hexatriene, the number of alternating double bonds increases. This means the extent of conjugation increases. The image also shows the orbital energy diagrams below each molecule. In ethene, the energy gap between the pi star to pi star orbitals are relatively larger, so more energy is required for excitation. In butadiene, conjugation increases, which lowers the energy gap. As a result, lesser energy is needed. In hexatriene, conjugation is greater, so the energy gap becomes even smaller. This causes absorption at a longer wavelength. The graph in the image clearly shows this increase in wavelength. This shift toward longer wavelength is called as redshift. This concept is extremely important because it helps chemists estimate molecular structure and identifying conjugated systems using UV visible spectroscopy. Now, let us understand how electronic transitions are connected to quantitative analysis through the Beer-Lambert's law. This law is represented by A equal to epsilon Cl. Here A represents absorbance, epsilon is molecular observability, C is concentration, and I is the path of the sample cell. The image shows UV visible radiation passing through a sample solution placed inside a cuvette. When this radiation interacts with molecules, electrons absorb energy and undergo electronic transition. Because some radiation is observed and the intensity of transmitted light decreases. This decrease is measured as absorbance. The amount of absorbance depends on the type of transition occurring. For example, pi to pi star transitions usually produce stronger absorbance while n to pi star transitions show weaker absorbance. The greater the concentration of the observing molecules, the higher the absorbance. This relationship allows us to determine the concentration of unknown samples accurately. This is why Beer-Lambert's law is widely used in pharmaceutical analysis, environmental monitoring, and biochemical studies. This slide shows how electronic transitions are observed experimentally through a UV visible absorption spectrum. The graph shown here plots absorbance on the vertical axis against wavelength on the horizontal axis. Each peak in the graph represents absorption of radiation caused by electronic excitation. The most important feature is the highest point known as lambda max, which is the wavelength where maximum absorption occurs. This gives important information about the molecule. The height of the peak represents the intensity of absorption. A taller peak usually indicates a more potable electronic transition. The position of peaks helps us to identify structural characteristics such as conjugation and functional groups. As shown in the graph, different compounds produce different absorption patterns. That is why UV visible spectra are often called as molecular fingerprints. By studying this spectra, chemists can identify compounds, estimate concentration, and analyze molecular structure. This makes absorption spectra one of the most powerful tools in analytical chemistry. This slide highlights the practical analytical applications of electronic transition. The lab analysis image shown here represents how these concepts are applied in real chemical laboratory. Using UV visible spectroscopy, electronical transitions helps in compound identification. Since every organic compound produces a characteristic absorption pattern, it becomes easier to identify functional groups and conjugated systems. Electronic transitions are widely used for quantitative analysis. Using observance measurements, Beer-Lambert's law, we can determine the concentration of unknown solutions accurately. Another major application is structural analysis, where absorption wavelength helps predict conjugation and molecular environmental. In pharmaceutical industry, UV visible spectroscopy is used for drug testing, purity analysis, and stability test studies. It is also used in environmental monitoring to detect pollutants and contaminants. In biochemical analysis, it helps studies protein, DNA, and other biomolecules. So, this slide shows that electronic transitions are not just theoretical concepts. To conclude, electronic transitions explain how organic molecules observe electromagnetic radiation. We studied the four major transitions and their energy requirements. We also saw how conjugation influences absorption behavior. Most importantly, we learned that these transitions form the foundation of UV visible spectroscopy. Understanding these concepts allow us to interpret molecular behavior and perform analytical measurements effectively. This makes electronic transition a fundamental topic in analytical chemistry. Next, acknowledgement. I sincerely express my gratitude to Dr. Sanjay Kumar, Assistant Professor, Department of Chemical Engineering, for his valuable guidance and encouragement. And reference. These references are used in preparing this presentation. The concepts were referred from a standard analytical chemistry and a spectroscopy textbook along with the reliable scientific educational resources. The visuals and diagrams were adapted from open source chemistry references and educational materials. And finally, thank you all for your attention.